Hello, today we're going to look at the Piezo Motion range of piezo motors, both linear and rotary, available from Motion Control Products in the UK. Hello, my name is Tony Robinson, and today we're talking to Nick Copley of Piezo Motion about the Piezo range of products. Hello, Nick.
Good afternoon, Tony. How are you?
Maybe you could start by telling us something about Piezo Motion. Who are they and what do they do?
Sure. Thanks for the time to be here with you today, Tony. Piezo Motion is a US company. We spent a number of years working in the precise motion space and a lot of time investing in R&D around the piezo technology. And we've brought to market now this range of products, linear and rotary motors that obviously MCP are representing here for us in the UK.
Yeah. So you threw away around the word piezo. What actually is piezo? What does it mean? What's it about?
So piezo is an interesting technology. It's actually discovered in the late 1800s by the Curie brothers. And it's the characteristic of some materials whereby if you put an applied force or a squeeze on them, they actually emit a electrical current or electrical output. And then the reverse of that is also true. If you actually apply electric current to them, they will change shape and actually grow or shrink. And we use that behavior to drive motion products. So what we can do is put a high frequency oscillating waveform onto the piezo crystal. The tip on the piezo crystal will then start to oscillate. We can use that by pressing it against a linear or a rotary bearing system and create a motor to create motion.
So you use the reverse piezo effect, and basically by applying voltage at a frequency, you either compress or expand the crystal size and basically move it along a surface.
That's correct, yes.
It's a friction drive.
Yeah, there is a friction contact between the tip of a resonator and the drive surface which is pushed against. And then we can either drive it at high frequency with a kind of constant resonance, so it puts a lot of energy into the system and pushes it forward, or you can make small incremental steps.
So these are the resonators here in front of us?
That's right, we've got three sizes that currently develop. The smaller one in linear systems will create about a 0.3 Newton drive force. The middle one is around a 4 Newton resonator and the big one's around a 10 Newton thrust.
Okay, and what type of applications would you tend to use these in?
So they're a very versatile product. Really, most places where you kind of find good quality DC motors and stepper motors for positioning and control applications are an ideal potential. We see a lot of kind of potential in things like optonics, photonics, optometry, optics and laser systems for positioning of mirrors and the like. Really, any kind of micro positioning or positioning applications are a good candidate.
So really high resolution precision applications?
Typically, yes, because these resonators can be made to take small incremental steps down to about 50 nanometers per step. So on a rotary motor, for example, that can achieve around 625,000 steps for one revolution. And every one of those steps is at full torque, unlike a stepper motor where you start to microstep, you lose a certain amount of the drive torque to control the position. These will control at full torque that many steps in a single revolution. But they have other advantages as well, so lightweight, low energy consumption, very high speed in terms of the frequency response. So there's various different kind of characteristics which make them quite useful for motion.
We've said that it's a friction drive. How do you prevent slippage as it's rotating or going along the linear bearing? How do you prevent it from slipping?
So there is obviously a rated torque or a rated force. Typically, for example, a linear motor like this will have a 4 Newton thrust, and the blocking force of that friction system is a little bit higher than the thrust force. So typically about 10 or 15% higher. So maybe around 4.5 Newtons or so as a blocking force. If you exceed the force, then basically you will, as you described, get slippage between the friction of the resonator tip and the slide bearing. So really it's around designing the system so that you don't exceed the rated force or the rated torque of the motor.
Okay. And you said that the resonator tip obviously is a friction point of contact with a surface. Is that the main failure mode then wear on the tooth?
So that is exactly where we would kind of look out for a failure mode. But having said that, although there is obviously constant interaction between the tip and the drive surface, we have got very nice kind of lifetime experimental data that's been worked on over the years. So the rotary modes, we've had these doing upwards of 30 million cycles and still kind of operating satisfactorily. In the linear motors, we've had operating at 300 kilometers a stroke very, very satisfactorily. So for most motion and positioning applications, there's more than enough lifetime in the system. One of the advantages of this particular technology is that the tip is actually a monolithic part of the ceramic. It's all one piece. You do see in quite a few traditional piezo systems where the tips are additional components which are bonded or are fastened to the resonators. And that is a failure mode where they can fracture or crack or come free under certain operating conditions. And that doesn't happen.
Okay. And obviously, is heating an effect that's going to cause problems with these?
So in terms of the kind of advice for duty cycle, there is a recommendation that you don't exceed 50% duty cycle on the motors for applications. So that means you either run them at half speed continuously, or obviously the usage of operation is only about 50% of the maximum duty. If you do exceed that and start to run them too heavily, then you can get a heating effect on the resonator because you're putting energy into it constantly. And if it gets too hot, then you can effectively have what's called a depolarization, where the alignment of the crystalline structure degrades, and then you start to lose the piezoelectric effect.
Okay, I understand. So you've got to be careful not to exceed that threshold temperature, otherwise basically the crystal will decay.
That's right, but we find for most positioning and motion applications that are around kind of position control, duty cycle is rarely kind of constant. So for example, this type of motor is not suitable for fans, blowers, pumps, where you're continuously running at high speed or high load. It's more kind of intermittent or low frequency duty or low speed duty.
I notice we've got some PCBs here. Are these your control boards?
That's right. Each piezo motor will have a driver board with it. And the function of the driver board is to translate control signals to the necessary high frequency signals at higher voltage that will actually be applied to the piezo ceramic to make it oscillate in the way we need it to. These crystals are actually fairly low in terms of the voltage compared to a lot of conventional piezo. Often piezo ceramic systems are running at hundreds of volts. These actually operate around 60 or so volts for the main oscillators, which is quite modest in terms of the output drive voltage. And they're running at frequencies of between about 140 and 300 kilohertz, depending upon the size and shape of the motor.
Oh, that's interesting. And if a customer wanted to take one of these units and then kind of embed it into his own machine or his own system, how easy is it to customize the units and allow him to interface to it?
That's a really good question. So I think if you look at the kind of portfolio, we have a range of standard products, different sizes of rotary and linear motors, with encoders, without encoders. But one really good way of thinking about this as a core technology is that we have the kind of resonator family, which is able to create motion. And they can be designed into OEM products with different bearing sizes, different rotor sizes, different linear structures, different encoders to create, like you described, a very integrated OEM design that can fit inside a customer's instrument or device very accurately and very neatly to perform just the function he needed to.
So the customer had to say a wearable piece of equipment that he wanted to use. He could customize the unit into it very, very, very easily because you've got basically components you can slot together to produce a solution.
That's right. We can consider it as a kind of set of components and a technology architecture that we can customize and apply to whatever the customer needs, really.
And what type of software would he use to interface to it?
So the driver boards have got a very simple architecture, and they all have 3 pins for motor control. There's a ground pin, and there's a pin for right and a pin for left, or clockwise, anti-clockwise. And that can be very simply controlled with a TTL signal, high or low. High means drive, 0 means stop. And you can PWM that to get the kind of mark space ratio and the frequency you need to get the rotary motion applied. Or there are versions of the encoders where we have additional firmware that can get much tighter and more precise motion control from either serial commands, or there is a graphical user interface that the customers can use that sits on Windows 10.
Okay, so a number of different methods you could actually interface with.
That's right, and obviously the customer can integrate this into their own control environment as well if needed. We can talk about kind of schematics and firmware licensing to embed it into say an onboard PC in a device or instrument.
Okay, and then he would use his own software interface for that.
That's right. Yeah.
Okay. Oh, well, thank you for your time, Nick.
Thank you very much, Tony.
Thank you for watching. I hope you found it useful. If you've got any questions, please feel free to contact us. Thank you.
Thank you.